So, in the last lecture, if you remember, we talked about the low cycle fatigue which happens in this region. So, low cycle fatigue basically means the stresses are more than yield strength, and in that region usually it happens because of the thermal strain, and so we take the plastic strain because there will be plastic strain because the stresses are higher than the yield strength, and we plot it against the number of cycles, and then we can arrive at such an equation which relates the plastic strain amplitude with the number of reversals, or in other words number of cycles to failure. So which is called Coffin-Manson's law. In today's lecture we will talk about this region which is high cycle fatigue. So, our stresses will be smaller than the yield strength, therefore, we will have only elastic deformation in the material. So, as they say in nuclear materials or nuclear physics, that there is no safe dose for radioactivity. So, any dose is harmful for the health of human. Similarly, no damage or no deformation is safe for any material, and the greatest example of that would be high cycle fatigue. So, what we have in high cycle fatigue is our stresses are lower than the yield strength, and so therefore, the deformation is completely elastic. So, it can be sigma max. So, it is sigma max because if we plot sigma A, then it does not mean to draw a line of yield strength on this plot. So, this is sigma max versus number of cycles for the failure. So, even though the stresses are elastic, which is completely reversible, we still have damage in the material. So, the question is that why do we have damage? Because elastic energy is reversible and it does not deform the material completely or permanently. So, why would we have damage in the material? So, that is what we will try to understand today, but before we go there in the mechanism of what happens in the high cycle fatigue, one thing for sure we have to understand that this happens at the amount of stresses which are lower than the yield strength. So, we are talking completely about the elastic regime of the material, and these things we are discussing for metallic materials. So, we are still dealing with linear elastic materials and not non-linear elastic materials. So, when we have such deformation in high cycle fatigue, then instead of relating the plastic strain amplitude which we did in the low cycle fatigue case, we relate the amplitude of the stress sigma A, which can be written as the amplitude of the elastic strain divided by 2. So, the range of the elastic strain divided by 2 will be amplitude of elastic strain into E. So, sigma A divided by E will be delta epsilon E by 2. Okay. So, this should be very simple to understand, this part of the equation, and this can be related to. So, we had a similar parameter in Coffin-Manson's law where we had epsilon f dash. Similarly, we have sigma f dash into 2n, and there we had a power of c. Here we have a power of b, and these equations. So, these values b and c are not arbitrary or not random. So, the previous one which, so let me write that equation also, so that you will have a revisit to that equation. So, for high, so this is for high cycle fatigue which we are discussing today, and this equation was for low cycle fatigue where we had E f dash to n to the power c, and this was for low cycle fatigue where we had plastic strain involved. In this case we only have elastic strain. So, This power C and B obviously do not have any origin of meaning there, but it is so because this equation was given by Coffin-Manson, and so the C there somehow resembles Coffin, and B is there because this equation was given by Baskin, and so this is called Baskin's equation, and therefore you have a power of B. So, I am not sure that if these symbols actually represent the inventor's name, but they somehow are in accordance with that. So, looking at these two equations of high cycle fatigue and low cycle fatigue, maybe we can define the whole curve if we superimpose these two equations. So, what we will have in any fatigue cycle is that we will have certain amount of strain amplitude. Even if we have stress amplitude, we can change it to strain amplitude by following some relationship. So, assume that we have strain controlled fatigue. So, we have strain amplitude, and that we can break in elastic part plus plastic part, and then for this part we can use that, we can replace with that, and for this part we can replace with that. So, we will have sigma f dash into 2 n to the power b, right, divided by E. Yeah, yes. So, that will go that side, plus in this case we will have E f dash into 2 n to the power c. So, there is this difference that there is no Young's modulus in this case, because we are obviously talking about plastic deformation here, and here it is elastic deformation. So, we have elastic modulus in the equation. So, we can have such an equation which can describe the whole curve of the fatigue life, which is elastic plus plastic both. So, this equation basically should be applicable to the whole curve. So, if you plot the behavior of the material, so we have strain amplitude on log scale here, and we have so n, so we can plot log of n, so number of cycles to failure, and the curve actually will look like this. So, here I am not drawing any line which will show you fatigue limit, because fatigue limit is only happens to few materials, especially steel, especially BCC alloys, and for other materials we do not find the endurance limit or a constant line like that. So, and even for steel, we have discussed this before, that even for those materials for which fatigue limit is defined, it is not true. So, the fatigue limit actually does not exist even for those kind of material, but you will have to go longer on x axis to achieve that, so to see that. So, on this curve, if you just plot the plastic part of the equation, so plastic part of the equation is this one. So, if you plot that, then that line, if you remember the last curve, will look like this, because in that part we had an equation where we plotted only plastic strain amplitude versus log n, and that was something like this, right, and the intercept. So, the slope of this curve will be c, because we are plotting log log. So, the slope of this curve will be c, and the intercept will be log epsilon f dash. So, this is my plastic curve or plastic part, plastic strain part. and then if we draw the elastic one, so this part, then we will have something like this. So, this is this one. So, again because we are plotting log log, so you will have the slope of this curve as b and the intercept will be log of sigma f dash by e. So, this is my elastic part of this equation, and you can find out the intersection to find out the transition, when the transition happens from elastic to plastic. Okay. So, that can be done, and that is not very important at this point of time, but that is possible. So, you can take two equations. So, one equation will take only this part, another equation will take that part, and then you can find out the intersection of those two lines, and then that is how you can find out the point of transition. So, that is very simple mathematics. So, I will leave it to you for your own practice. And so in these equations it was assumed that sigma mean is 0. So, there is complete reversal, but if sigma mean is not 0, as we have seen in many of the cases that so for example, our maximum stress is 200 megapascal, minimum stress is 20 megapascal, then our mean stress is not 0, right. So, our mean stress will be 220 divided by 2 to 110. So, that is obviously not 0. So, in those cases what will happen, so for that case we will have to modify the equation. So, in this case where this is related to stress, we can modify that by making an offset, right. So, for instance, we have for this equation we assumed a stress profile something like this, right. So, the mean was this, which is 0, and then you go to sigma max and sigma mean. If we have a cycle which is here, so our sigma mean is there, then what we need to do is we just need to shift this curve by sigma m amount, and that is what we are doing. So, what we are doing is we are making an offset here and the law remains the same. Okay. So, this can be done when the mean stress is not 0, and then in order to unify the high cycle fatigue region, which is this part, and the low cycle fatigue region, which is that part, Manson from Coffin-Manson again proposed another equation without any so not much of a theoretical proof, but empirical proof is something like this, where you have so sigma u divided by E into n to the power 0.12 plus E f to the power 0.6 into n to the power minus 0.6. So, this is there is no theory behind this equation, this is just an empirical equation. So, Manson did a lot of experiments and he fitted the data and found out the values in this form, and this is a simple equation because you do not have to plot the log and you have to find out. And another importance of this equation is that you can find out the strain amplitude. If you have the strain amplitude, you can find out the number of number of cycles required to fail by just doing a tensile test, okay, not fatigue test, but tensile test, because this sigma u is the ultimate tensile strength of the material and epsilon f is the failure strain of the material. So, this gives you a very important relation between tensile data and the fatigue data. So, of course, the behavior of the material So, the material is same. So, there has to be some relation with the monotonic behavior of the material and cyclic behavior of the material, and although they are not same, but by doing experiments Mansion found that this kind of relation can be achieved, and it can tell you, it can be used to predict the fatigue life of the material. So, now we will discuss that why, even though stresses are lower than the elastic limits, how come the material gets damaged and ultimately fail. And so, what happens is that in the material you have a lot of inhomogeneities, you have a lot of inclusions and voids and carbides and other particles which are undesired, but they are there. It would be wrong to call them undesired, because sometimes they are desired. Sometimes we deliberately put them, but when we do not put them deliberately, then they become undesired, although it is not necessary that they will harm the material. Nevertheless, the point is that the material is not homogeneous at the microscopic level. So, even if you do not have any defect in the material, you will still have grain boundaries which will act as a defect. Even if you do not have grain boundaries, you will have dislocations, and those dislocations will be stopped at some point of time, and then they will not be movable. So, they will be sessile, and once that happens, the deformation starts getting stacked at that point of defect, and because of that the damage will increase. The first observation and the most important observation of fatigue is that the fatigue starts from the surface, although this is not completely true, but for the high cycle fatigue and low cycle fatigue reason, this is the truth, that the damage, the crack starts in case of fatigue from the surface. And this is why when we do fatigue testing, we make the specimen mirror polish. So, we do not want any roughness on the specimen, because that, so for the same, so for example, I have tested for the same material. So, let us say this is my specimen and I did the testing of, so for example, this is SS 316L. So, stainless steel 316L steel, and we did the fatigue testing of that, right. And then another guy did the fatigue testing of the same SS 316L, but they will get two different values for the whole fatigue data, and that, so of course you have a lot of scatter in the fatigue data. So, what you do is you do a lot of tests and then you plot the SN diagram. So, you plot sigma max versus number of cycle to fail. So, you will get a lot of data which will be highly scattered, and then you apply some statistics. So, for example, Weibull distribution, and you find out this equation, a unified equation which we just studied. So, for example, epsilon by 2 is equal to sigma f dash divided by E 2n to the power b plus epsilon f dash into 2n to the power c. So, something like this we find, or we may find something like what Manson gave. So, some empirical equation. Now, another guy does the same test. So, those many number of tests on the same material, and if he is not able to find an equation which does not vary by which varies by a significant amount, then there is a problem. So, this scatter is coming obviously because of the statistical nature of fatigue, but apart from that there will be another contribution which will be due to the surface finish of the material. And to avoid this, so for example, if my surface is more rough and the other guy's surface is less rough, then the chances of fatigue failure in my specimen will be more in comparison to that person, and this is not a material property, this is the surface property because of which this will be happening. and we do not want to include the problems of surface to be reflected in the material's property. We do not want that to happen. So, what we do is we make the specimen mirror polished, okay, and then we do the testing so that everyone gets the same behavior for the same material tested. Of course, there will be some differences in the values which if you do the testing at different labs, because it depends upon which stock of the material you have used. So, for example, SS316 is made by, for instance, Bardhaman Steel or Tata Steel. So, those two companies will be making the same steel with different amount of impurities. Okay. So, that obviously will result in a different amount of equations and different fatigue life of the material. It does contribute to the material property, but if you can avoid some scatter, then we must avoid this, and therefore, the standard procedure is that you have to mirror polish your specimen before testing them, and that is what is done. So, and it is not done in tensile specimen because tensile damage does not start from the surface, but fatigue does starts from the surface. So, we do not want to have the surface roughness in the specimen. All right. So, now we do not have specimen roughness, we have polished it to the limit which is also economic and also not very effortful to do. So, we do that. So, what will happen in that case? So, the material, for instance, you are applying some stresses, and we know that usually the deformation happens because of shear stress, right. So, I have a dislocation like this. So, an extra half plane which is absent downwards, and I am applying a shear stress. So, this dislocation will go on the surface, and on the surface there will be a step formation. This much we know, right. This will happen in monotonic loading, right. In fatigue loading, what will happen is that because once you are applying a stress in this direction, and in the second cycle you are applying the stress in the reverse direction. So, what you will have is you will have step formations which may result either in this kind of notches. So, these are all different dislocations which have ended up at the surface, or it can be grain boundary also, and because of the reversal of the stress, some of the dislocations ended up not there, but a little smaller in the distance. So, you will have a notch kind of geometry formation or shape formation. Opposite can also happen. So, you can have a ridge formation. So, you can have something like this. So, here this is happening at an atomic scale, okay, because these are one step. So, this dimension is one atomic distance, okay. So, this is happening at an atomic scale, and if it acts as a notch, then you can imagine that there will be a plastic zone here, okay. So, we have studied that in fracture mechanics, that if you have a sharp crack tip, you will have the stress will increase at the tip of that crack. So, you will have a plastic zone here, right, and therefore, now you can realize that even though the stresses are smaller than the elastic the yield strength, locally you can have plastic deformation, okay. So, there will be some plastic deformation, and then this plastic deformation will be accumulative. So, in each cycle this plastic deformation will get more and more deformation in it, okay, and this results in a initiation of crack. So, this is not necessarily happening at the surface. It can happen at the grain boundary, it can also happen inside the grain, where the dislocations are pushed too close to each other that they become a micro, a very, very small crack, a crack of a atomic scale. Okay. So, similar thing can happen at the barrier of the dislocations, and therefore these. So, what I said just now is that it's not necessarily that it is happening at the surface, it can happen also inside the surface, but inside the surface there are recovery methods also. Alright. So, for example, if there is a lower cottral barrier, so one dislocation is, so dislocation has broken up into Shockley partials and they are coming along this on this 1 plane, and then there are another Shockley partials which have dissociated. So, one dislocation has dissociated into two Shockley partials and they are also coming on different 1 plane, and they intersect on another 1 plane and it becomes a lower cottral barrier. So, nobody can move from here. So, once they have arrived here, more and more dislocations will be getting piled up, right. So, this is happening when the stress is working in this direction. If I reverse the stress, some of them will be able to move in the reverse direction, right. So, in each cycle there will be some dislocations getting piled up here and some will be getting removed here. This barrier can be broken depending upon how much is the stacking fault energy of the material, at what temperature you are deforming the material, how much stress you are applying, so on. All those reasons will be contributing to the annihilation of these barriers, and it may happen that this barrier will be broken and the dislocations can cross slip to another plane and further move from there. But surface, there is no recovery procedure. So, surface, once there is a damage there, that is not going to get recovered, and therefore, what happens in this region, that the damage starts at the surface and that is not recoverable. So, it propagates, the crack propagates, and then you have, at the end of the day, you have the failure, right. And as we discussed before, for some materials we get endurance limit, right. So, this curve becomes constant, meaning that you apply infinite number of cycles and the material will not break. And research has been done for these materials also, where it appears that the material has infinite amount of cycles. So, they become immortals. But after doing the fatigue cycle for more than 10 to the power 9 number of cycles, it was found that they also fail and this limit starts decreasing. Okay. Apart from this, what else was found, that in this case where at very high number of cycles, when the material fail, they do not fail because of the damage from the surface, but they fail because of the damage which comes from inside. Okay. So, what is happening there? The problem is that, as I said, no nuclear dose is safe, but still there are safety guidelines which says that, for instance, if you are in the range of some becquerel of radioactivity, you can work for 8 hours. If the radioactivity increases, you can work for 2 hours. And for example, in the Chernobyl accident, the people who were going on the blasted area to take the graphite and other broken pieces from the roof of the building to drop them on the earth so that they could collect it and they could dump it somewhere. So, for them, because they were very close to a blasted nuclear reactor, the safe time was calculated to be 8 seconds or 10 seconds or so, if I am not wrong. So, that time was very small. So, they used to go in the set of 8 to 10 people and they have to come back. So, they will just push some graphite from the roof downwards, and they will run and come back within 20 seconds, and the next set of people will go. So, what I am trying to say here is that there are safety guidelines, and they say that you have a safe time, and if you go in this time you will not have any damage in your body. But then the research has found that there is no safe dose for radioactivity. So, even if you go for a smaller time, the damage is there, but that will result in a crisis after a very long period of time. Okay. So the damage is insignificant. Similarly, if I am applying a cyclic loading on my specimen, then damage is not only happening at the surface, but it is also happening inside. It is happening at the grain boundaries, it is happening at the lower cortical barriers, it is happening at the inclusions, but those are getting recovered. Even then, not complete recovery is happening. Okay. So, there are damage in the material is still getting damaged, but those will not propagate into a failure until this point. If you keep on doing this, then imagine the damage which has happened in the material. That damage is getting accumulated for 10 to the power 9 number of cycles, and when you go there, then this damage is so big that it leads to a failure. So, what looks like the material is immortal also fails, because you still have damage inside. So, it is not breaking from outside, from surface, but it breaks from inside. So, the stresses here are so small that the surface damage is not going to lead to failure, but because you have applied so many number of cycles, the damage which has happened inside the material will result in failure. Okay. And this is a recent research which, so we have this part of the fatigue life which is called low cycle fatigue, because the material breaks at less number of cycles. Then you have high cycle fatigue, where material breaks at high number of cycles at lower stresses, and this range where the new research found that material still breaks and material breaks from the damage inside is called very high cycle fatigue regime. So, this is called very high cycle fatigue, or giga cycle fatigue, or giga high cycle fatigue also, but there is no point in calling it giga high cycle fatigue. Giga means 10 to the power 9 cycle fatigue. Okay. So, that is a new research, and which showed the world that there is no endurance limit of any kind of material. There is no fatigue limit truly, but you can call it fatigue limit if your component is not going to be used for more than 10 to the power 8 number of cycles. If